All right, now we're ready for the second part of our lecture about sampling techniques that we might use in fish management. And we're going to spend this part of the lecture talking about electrofishing. Basically, electrofishing induces involuntary muscle spasms in the fish, and the fish loses its ability to maintain its buoyancy and its position in the water column, and it floats to the surface, and you can pick them up. Of course, they recover pretty quickly, and there are always some mortalities, but usually mortality is pretty low as far as the sampling method goes. Mortality will be higher when you're electrofishing in colder water. Also, if you've got a longer fish, like a muskie or a pike, because they've got really long muscles along their spine, and when those long muscles contract, they're so strong it can break their back. So a lot of times if we're electroshocking and we roll a muskie or a pike, we'll get off the pedal and give them a chance to escape, or usually don't use electrofishing for sampling those fish for that reason. Also, AC versus DC has much higher mortality. We'll talk about this later, that AC hits them harder, stuns them longer, but you do get a little bit higher mortality. Given that, mortality is remarkably low, and this is a really excellent way to sample fish. Now, there's a little bit of bias. The electrofishing does not seem to work on very small fish and on very large fish. So you're kind of biased against the very small and the very large. The very small fish, there's not a big enough voltage drop across their body to really have an effect. And so a lot of times you'll see really small fish swimming through your field and they don't seem to even notice it. Really large fish, when they initially are shocked, their muscles can spasm, but their muscles are so big a lot of times that will propel them outside of the field where they can quickly recover and escape. So that's supposedly one way that we're biased against very large fish. Another thing about very large fish, they have a bigger voltage drop across their body. They absorb more energy when they are shocked, and so they are hit harder by the electroshocking and they're stunned harder than a smaller fish. Given all this, electrofishing is, of course, very popular, very useful. It has probably the least amount of bias relative to a lot of the other gears. So we get a wider range of species, and we get a wider range of sizes and ages than you would with other gears. Every sampling gear is going to have some kind of bias. Every sampling gear is going to be better in one area versus another. The point of these lectures is that we talk about all these different biases, and so you know what you're using, and you know which is an appropriate sampling method for your particular situation. Okay, so let's talk about boat electrofishing. Of course, is the most common kind that we do. You need a minimum of a 5 kilowatt generator. One factor that's going to influence the ability of your electroshocker is water conductivity. Of course, conductivity is exactly what it sounds like, the ability of the water to conduct an electric current. Clearly, that's going to influence how well your electrofisher works. If the conductivity is too low, very clear, clean water, then you're not going to have enough power. You're not going to have enough energy in the water to effectively shock fish. And so if the conductivity is low, you have to crank up the voltage to try to get more power into the water so that you can get a sufficient level of power to actually shock fish. In the opposite situation, where you've got water with a lot of dissolved ions in it, if the current's too high, a couple things could happen. One, the current's going to follow the path of least resistance. And if the water conductivity is super high, the current's just going to flow around the fish instead of flowing through the fish. And so again, you're not going to be as effective when you're electroshocking. Excuse me. Another thing that might happen if the conductivity is so high it's kind of like a short circuit. It's kind of like just touching the wires together, and so you're going to get too high of a current, too many electrons flowing, and that will cause the breaker on your generator to trip. And so you'll have to keep resetting the breaker. The solution there is to maybe turn the voltage down a little bit, but you can only reduce voltage so much. You have to have some voltage running. A better solution is to reduce the number of droppers. So take some of the droppers and zip tie them out of the water, or reduce the amount of the dropper that's in the water. So pull the droppers up so not so much is hanging in the water, and then you can avoid some of these problems with very high conductivity water. When the conductivity of the water matches that of the fish, that's when you get the most efficient electrofishing, because the current's going right through the fish. I want to say that a rule of thumb here is 300 to 400 microsiemens per centimeter. That number sticks in my head. I think it's pretty close to that's the average conductivity of a freshwater fish. And so if your water conductivity is around there, you're going to be getting very good electrofishing. Okay, let's talk briefly about the physics of electricity, because I think it's important to understand this to understand what your electroshocker is doing. So of course electricity is just flowing electrons. Electrons, normally you've got a wire and the electrons move through that wire from point A to point B. Of course in our electrofishing scenario, the electrons are flowing from the generator down a wire into the water, through the fish, back up a different wire, or back up into the boat's hull, and then making their way back to the generator, completing the circuit. How hard the electrons are thrown, or how much punch the electrons have, is called the volts. Okay, so if you think about an electron, and when I say the electron is being thrown, that's kind of the metaphor that I use. You know, we burn gas in the generator spins, creates an electric field, a magnetic field. That magnetic field then forces the electrons to move down a wire. And so if the electrons aren't being pushed very hard, that's low voltage. And so imagine if you took an electron and you threw it and it bounced off the wall, it would just kind of barely bounce off the wall. That would be low voltage. Whereas you have that same electron and you're really whipping it, that would represent higher voltage. So voltage can be thought of as sort of the punch that the electrons have. Current, which is measured in amps, which is represented by I, is how many, it's the number of electrons that are moving past a point in a given time. And so current doesn't have anything to do with how hard they're being thrown, it's just the sheer number of electrons that are flowing. So when you talk about current, it's how many electrons are flowing through that wire or through the water. Resistance, which is measured in ohms, represented by R, is how much the water or the wire or anything resists electron flow. So it's the opposite of conductivity. Conductivity is how well it conducts electric flow. Resistance is how hard it resists electric flow. And these three values are all related by this common equation, I equals V divided by R, or V equals I times R. Another metaphor that we often use for understanding electricity is kind of the pipe metaphor, or the garden hose metaphor. And so the pipe or the garden hose represents a wire, okay? And so electrons move through the pipe, and how hard you throw them into the pipe, that represents voltage. And so if you've got really high voltage, when they come out the other end, they're really going to shoot out the other end. Whereas if you've got low voltage, you take one electron and you just kind of plunk it in there, and when it goes to the end of the pipe, it just kind of falls out. That would represent low voltage. Whereas the number of electrons you throw down that pipe how many, that's going to represent current. And if you think about it, the size of the pipe or the garden hose is going to influence how many of those electrons you can throw down the pipe. Okay? So if you've got a really narrow, small pipe, you can only cram so many electrons in it at a time. And so you can only really get so much current flowing through that. And so in a smaller pipe or a smaller wire, the resistance is higher. Why is the resistance higher? Because there's only so much room for the electrons to move. And if those electrons are all jammed in that small wire, they're bumping into each other, they're bumping into the sides of the wire, there's friction there, that impedes their movement. And of course also if you get the friction, that's going to turn into heat. And you know, if you take a very small wire and you hook it up to a large power source, force a lot of current through it, what happens? The wire gets very hot and it can start to smoke and catch on fire. Whereas if you use a bigger pipe, a bigger wire, the electrons have more room to move, and so you can shove more electrons down that pipe. It can carry a higher current. So that's why if you look at the wires coming off your battery in your car, or the wires that are carrying the electricity away from the generator in your electroshocker, it's a pretty stout wire so that it can carry a lot of current. Consequently, if you have what's happened to us before on our boat is if you've got a spot maybe where a plug attaches or something where the wire starts to rust, and a lot of those wires, a lot of the smaller wires in your cable rust away to where all that electricity is being forced through one or two strands of wire, the resistance is very high. You're going to get a lot more heat given off, and you can have a fire hazard. So that's how these concepts are sort of related. Now, if I equals V over R, so the amps is the volts divided by the resistance. If you increase the voltage, the current should go up. If the resistance stays the same, so say you're in a lake, and so your conductivity is pretty much constant throughout that lake, so basically your resistance is the same, and you crank up the voltage on your electroshocking box, well, the amps should also go up. So cranking up the voltage, putting more punch in those electrons, will also send more electrons through the water based upon this relationship. So that's why if most of your electroshocking boxes have an ammeter on it, and if you crank up the juice coming from your generator, you can see the amps go up. And so higher volts means higher amps. By the same token, if you decrease resistance, which would be the same as increasing conductivity, the amps also go up. So if you kept the voltage the same on your electroshocker, and then you picked up the boat and went to a different lake where the conductivity was higher, you're going to have higher current running through the water with the same voltage, because it makes sense, right? The water can carry a current better, so you have higher current. Now, does this go on forever? That is, if you just keep cranking the voltage up, will the current just keep going up and up and up? And so we get this really massive generator, or we take our existing generator and we just keep turning the dial and turning the dial, putting more and more volts into the water. Will the amps continue to increase? And the answer is no, they won't. There's something called back EMF, or back electromotive force, and I think this is a force that occurs because, as you get more and more electrons flowing electrons generate their own magnetic field, and I don't quite remember exactly what back EMF is, but I know that at some point when you get so many electrons flowing, when you get such high current, that the back EMF will actually start as a force that will sort of push back and will limit the number of electrons. And so you can't just keep cranking up the voltage and watch the amps go up. At some point, the amps are going to max out. Another reason that you can't just keep cranking up the voltage on your electroshocker and keep watching the amps go up is something that we talked about earlier. If the amps get too high, if you get too many electrons flowing, then the breaker on the generator is going to trip. So even before the back EMF starts to kick in, if you have high conductivity water and you crank up the voltage and the amps really start, the electrons really start flying and the amps get really high, you can trip a breaker and then shuts the whole circuit down. Now, another important concept here is the concept of power. Power is measured in watts. Power is calculated by volts times the amps. All right? So think of power as how much energy you're putting into the lake. How much energy is going into making those electrons move. That's power. Okay? That's why it kind of is an important concept. If you increase the power, then you can increase the voltage and the power is going to go up. And of course that takes more energy. Or you can increase the current, or both. Any combination of these is going to make the power go up. Again, if you think of power as how much energy goes into moving electrons, if I have some electrons and I'm just kind of tossing them, that's low voltage, doesn't take a lot of energy. Same electrons, if I'm really whipping them, of course that takes more energy, more power. By the same token, if I take one electron and I'm just tossing it at low voltage, that doesn't take a lot of power. But if I take 1,000 electrons and I throw them all, again, low voltage, I'm not throwing them hard, but I'm throwing so many, of course that takes more energy. Again, that's going to be more power. If I take a whole lot of electrons and I throw them really hard, that takes a lot of energy, and of course, again, that's going to be a lot higher power. That's the way you want to think about power. How does power come into play with our electrofishing? Well, say you've got a constant voltage. Say you have your Electrofisher and you just turn it to a certain voltage and you don't touch that dial. And you go to a different lake. It's just like I mentioned earlier. Different lakes going to have different conductivity, which means you're going to have different amps, right? So if I go from this lake to a new lake and I don't change the voltage, but the new lake has a high conductivity, that means I'm going to have a higher amps even though I didn't touch the voltage. Well, by this relationship, if I have the same voltage but higher amps, the power has to go up. And so if the conditions change, I can have a change in power. Well, if power is how much energy or effort you're putting into the water, that means that this could be a non-standard effort. Okay? Of course, we always want to standardize our effort. One way that we always standardize effort is how many fish you get per hour. Catch per unit of effort is often in fish per hour. And of course, we do that with electrofishing. But we also might want to think about the fact that, well, if I don't always put the same power into the water, I'm not always putting the same effort into the water. And that's the idea behind something called power transfer theory. And power transfer theory is basically trying to argue that not only should you worry about how much time you let the Electrofisher run, but also you should worry about how much power you're putting into the water, because that's going to also dictate how much effort you're putting in toward catching the fish. And if you don't worry about this, as you move from lake to lake, you never really know how much power you're putting in from one lake to another, and so you don't really have standard effort. That's the idea behind power transfer theory. So what we want to do is always put the same power into the water. So if you're not thinking about power transfer theory, what are you often doing? What we tend to do is drop the boat into the lake, fire up the generator, turn it on at low volts, crank up the volts until we see the maximum amps. And once we get the maximum amps, that's it. That's what we're going to run at. And so no matter what the conductivity, no matter where we're at, we mess with the volts until we get the maximum amps, and then we do our shocking. And what we're saying is if we do it, that power transfer theory is saying, well, you're not trying to just maximize the amps. What you're trying to do is standardize the power. And power, of course, is amps and volts. And if you're maximizing the amps, is that always standardizing the power? That's what the idea is here. Okay. So if you put the same power into the water, your electrofishing effort is standardized no matter what the water quality, no matter what the temperature, no matter what generator or boat you're using. You're always putting the same power into the water and thus the same effort. That's the argument behind power transfer theory. Okay, so how is this going to work? You're ready to go shocking. You go out, you measure the conductivity and temperature of the water right at the surface. Of course, you're usually shocking right at the surface. The people who published this paper put a chart in their paper, and that's in handout, I think 16 that I gave you. I gave you a copy of this chart. And what our goal is a power of 3,000 watts going into the fish. And they based this upon a lot of sampling they did on the Illinois River, and they looked at various power levels, and when 3,000 watts go into the fish, that's when they calculated you would have the most efficient and the most standard electrofishing. So that's our goal, is to get 3,000 watts into the fish. But to get those 3,000 watts into the fish, you don't necessarily put 3,000 watts into the water. You put varying wattages into the water, and then based upon the conductivity and the temperature, that's going to always put 3,000 watts into the fish. So you get the chart, which is on handout 16. Let's say your water is 20 degrees Celsius and the conductivity is 315 microsiemens per centimeter. So you look those up in the table. The table says the target power is 3,319 watts. So that's what you want coming out of your boat going into the water. If you put that power coming out of your boat based upon this water temperature and this conductivity, so basically based upon the resistance that you're getting in the water, that's going to end up putting 3,000 watts into the fish. And then if you go somewhere else and you have different conductivity and or different temperature, you would have a different target power, but the theory is you would still be putting the same 3,000 watts into the water after accounting for the different temperature and conductivity. And so how do you do this? Well, you adjust your shocking box until the amps times the volts equals 3,319 watts. So you need to know the amps and you need to know the volts that are coming out of your box. You multiply them together. When you get this value, then you should be putting 3,000 watts into the water and 3,000 watts into the fish. Okay. Well, understand that not every unit is capable of this. For example, the Smith root box that we have has an ammeter on it, and so we always know what the amps are, and we can control the voltage when we turn the knob to increase the voltage and increase the amps, and it increases the power going into the water, but we don't know what that voltage is. And so you need a box that tells you both the amps and the volts to be able to do this, and sometimes you don't have that. Another caveat here is not everyone believes that standardizing power is the most appropriate way to standardize electrofishing effort. So some people think that this is the proper technique. Some people would argue that it's not the proper technique. As I said before, a lot of times what we'll do is turn on the electroshocker and crank up the volts until we get the maximum amps. And so no matter what our water temperature or conductivity, we're always trying to maximize the amps in the water. And of course, that's all we can do because our box doesn't read volts. But it turns out that if you look at the calculations from power transfer theory, that we in effect might be standardizing power. That if you look at if you were able to measure the voltage and compare that to the amps that we're trying to maximize, that in these high conductivity waters that we tend to fish, we actually are standardizing the power by maximizing the amps. So that's potentially we could all be doing the same thing without knowing it. There's a little gray area here, but this power transfer theory is used quite a bit, and so I thought it was important that you understand the idea behind it. Okay, let's move on. Let's talk just very briefly about AC shocking versus DC shocking. All generators are AC. So no matter what, if you've got a generator, it's putting out AC. But of course you can run that through a brain box and modify it and turn it into direct current. All batteries are direct current. And you can buy things that are, you can buy inverters. Maybe you've seen these that you plug into your cigarette lighter that will convert DC into AC, but they're really super inefficient. And we don't use those for shocking. One thing that's different about DC versus AC is that DC attracts fish. It's something called electrotaxis. Essentially, what happens is if the fish is, one side of the fish is the muscles spasm, and that causes the fish to flip, and then the other side spasms, and it causes the fish to flip, and it kind of forces them involuntarily to swim toward the electrofisher. And this is a kind of a subtle effect. It's not like the fish all start jumping into the boat, but it does work. And sometimes if you pay attention when you're DC shocking in a boat, you can see this. You can see fish on the surface, and they kind of make a big circle coming right at one of the probes. Okay, this is much more important when you're talking about something like backpack electrofishing. You actually rely upon the DC attracting fish, because a lot of times the fish are tucked up underneath snags or banks or something where you can't get in there. But if you put that probe down near it, it'll cause the fish to kind of swim out. So it's kind of a subtle effect. Another thing about DC is we often use pulsed DC. We don't just use a direct current running from one wire to the other, but we pulse it, which means it's on, it's off, it's on, it's off, it's on, it's off, it's on, it's off. And the number of pulses per second can be modified, and sometimes you can customize your pulses per second for a particular species or size range. So for example, lower pulses per second tend to get bigger fish. You also tend to get more catfish with lower pulses per second. Higher pulses per second, like say 120 pulses per second, you tend to get a lot smaller fish. One way that actually help people figure out that electrofishing would stun fish and bring them up is something called calling up fish. If you ever remember the old telephones that you used to see that were hanging on the wall, and you'd take the little thing off and you'd hold it up to your ear and you'd speak into it, and before they'd talk they'd always crank a crank on the side. Well, that crank is a little mini generator that as you crank it, it generates a small current which actually powered the phone. And some people took this crank out of the old phone and put the wires to it down in the water and cranked it, put that juice in the water, and fish would start to float up, specifically catfish, and they'd call that calling up fish. Turns out it's because that crank produced just the right pulses per second of DC current that would stun catfish and bring them to the surface. A little bit of fisheries trivia there. Probably the most common setting on the DC box is 60 pulses per second. That's kind of a nice catch-all setting. It turns out that your alternating current runs at 60 hertz. So I think hertz is has something to do with the waveform, the distance between wave peaks. And so at any rate, 60 pulses per second actually is very similar to 60 hertz AC. And so 60 pulses per second kind of gets you a very similar species assemblage and size range that you would get with AC shocking. DC shocking is less efficient than AC shocking, meaning you get less power per gallon of gas. And so if you really want to maximize your efficiency, you should be using AC, not DC. Probably a lot of this has to do with when you're boat electrofishing, you're taking the AC from the generator and converting it to DC, and that's got to be inefficient. You have to lose some of that energy to heat. So that's probably got something to do with it. As we said before, DC is easier on the fish. You get lower mortality with DC shocking, but you also don't hit the fish as hard, and you don't stun them as well. So when you're DC shocking, you'll see a lot of fish that'll get stunned, but then they'll jump up and swim off before you can grab them with the dip net. AC shocking hits them a lot harder. You do get a little bit, you get better efficiency, especially if you use a 3-phase generator. You can get really high efficiency. You can really put a lot of power into the water. The mortality is a little bit higher, but it's still not a very significant amount of mortality. However, a lot of places don't let you use AC shocking. Missouri, you can only use DC shocking. Here in Illinois, you can still use both AC and DC. The trend is to go more toward DC simply to reduce the mortality. I used a lot of AC in my graduate school, and in my experience, you really didn't get a whole lot more mortality, and you really did seem to get more fish. So there is that advantage to AC. Of course, here's our standard boat electrofishing setup. Realize that in general you've got the generator in the boat. As the generator spins, it pushes electrons, pushes them up a wire to down to a probe that's in the water. Oops. Okay, excuse me for just a second. Okay, sorry about that. Don't know why my screen just went funny. But anyway, here we're back to the boat electrofisher. So the electrons get pushed down a wire down into the water. And there are several different ways you can have your electrofisher set up. You can have the electrons flow through the water, through the fish, to a different wire, which comes back, and then this is going to be the negative wire coming all the way back to the generator. And in that way the circuit is complete. Realize that anytime you want electricity to flow, you have to have a complete circuit. And the electrons can flow between two wires and all the way back to the generator, or you can take this wire coming out of the generator, split it, so both of these are basically the same wire going into the water, and then the boat acts as the anode. So the electrons flow through the water back to the boat's hull, and then there's a wire from the boat's hull going back to the generator, again, which completes the circuit. A number of different ways you can have these set up. Of course, other ways you can electrofish are an electric seine or a backpack shocker. The electric seine is AC shocking. You can see the generator in the boat back here. I've never heard of an electric seine that's set up for DC shocking. You can get away with a smaller generator. You want a smaller generator. You can't lug around a 5 kilowatt generator. And that's because your electric field is going to be a lot smaller. The electric seine is really effective under the right conditions. Big advantage over a minnow seine because it doesn't snag nearly as much. Of course, your backpack shockers are going to be DC. That's so you can just carry a battery around in the backpack, and as I mentioned before, you can use the DC to pull fish out from their hiding spot. Okay, so that's electrofishing. There's a lot that goes into it, but I think we've talked about a lot of the basics of electrofishing, and that sort of wraps up this first part of different techniques we're going to use in fish management, wraps up our sampling gear. So that's all I have for right now. I'll see you later. Thanks a lot.